quiet visitor from beyond our cosmic neighborhood has crossed our skies, and artificial intelligence is poised to unlock its secrets. In early July 2025, sky-watching cameras from the Atlas survey picked up a faint, fast-moving point of light. This interloper, hailing from beyond our solar system, was designated 3I Atlas, the third confirmed interstellar object in recent history, and an ancient traveler that has roamed space for billions of years. What can AI reveal by analyzing its trajectory, composition, and origin? In this video, we apply advanced algorithms to dissect every bit of data and ask questions science has yet to answer. Don't forget to subscribe so you don't miss investigations like this. If you enjoy it, help us by sharing the video so it reaches more people. The 3I Atlas phenomenon isn't just another comet dropping by. Its speed, orbit, and chemistry defy astronomers' expectations. From the first alert, observatories worldwide and spacecraft in orbit have tracked its path carefully. Using that massive data set, our AI has assembled a new narrative. A tale of stellar ejections, exotic volatiles, and a voyage through interstellar space. We'll take you from its detection in Chile to its passage near Mars, examining every clue this wandering body has left behind. Get ready to dive into a mystery that blends scientific precision with awe, and join us as we try to fathom what secrets this visitor carries. AI analysis, data, patterns, and correlations. Origin and discovery. Our AI notes that 3I Atlas was first spotted by the Atlas telescope at Rio Hurtado, Chile, on 1 July 2025, when it was about 410 million miles from the Sun. The Atlas system automatically scans the sky for potentially hazardous asteroids. Algorithms identified a point of light moving unusually quickly against the stellar background. Its designation carries a 3 because it is the third known interstellar body, an I for interstellar, and the Atlas acronym for the survey that found it. The object ES interstellar status was confirmed by analyzing its path. AI models showed it follows a hyperbolic trajectory, an open orbit that doesn't bind it to the Sun. Processing orbital records reveals a pattern confirming its external origin. 3I Atlas approaches from the direction of Sagittarius near the galactic center. Correlating its path with dynamic models, the AI concludes the object was ejected from another star system millions or billions of years ago and has wandered through the interstellar medium until entering ours. Its orbit is almost retrograde, tilted roughly 175 degrees to the ecliptic. The AI found its arrival was a chance encounter with our planetary neighborhood. Size, speed, and orbit. The algorithms also looked at its size. Observations in August 2025 with the Hubble Space Telescope constrained its nucleus to between roughly 440 millimeters and 5.6 kilometers in diameter. The AI determined that its initial speed at discovery was about 221,000 km/h. As it neared the Sun, its velocity increased to roughly 246,000 km/h at perihelion on 30th of October 2025, matching gravitational predictions. The AI calculates that as 3I Atlas leaves, its speed will drop back to the same value it had on entering. Perihelion occurred at about 1.4 astronomical units, near Mars's orbit. The AI calculates that its closest approach to Mars was on 3rd of October 2025, about 29 million kilometers away. It also notes that 19th of December 2025 will mark its nearest approach to Earth, though it will still be roughly 170 million miles away, almost twice the Earth-Sun distance. Its hyperbolic orbit ensures that after this passage, it will continue out of the solar system for good in early 2026. Composition and activity. The AI detected unusual chemistry in 3I Atlas. Early images showed only a faint coma, raising questions about whether it was an active comet or a nearly bare nucleus. A few nights later, spectroscopic observations confirmed a coma rich in volatile gases. Algorithms reveal that its coma is dominated by carbon dioxide, CO2, and carbon monoxide, CO, with only trace water vapor. That's unusual, since most solar system comets release mostly water as they warm. AI linked this to the possibility that CO2 sublimates quickly, cooling the surface and delaying water release, or that its ices have different crystalline structures due to a different formation environment. Another curiosity is an unusually high nickel-to-iron ratio. Local comets evaporate these metals in roughly equal proportions. In 3I Atlas, the first measurements showed strong nickel emissions and weak iron. AI proposes that this imbalance might reflect the sublimation temperatures of its metallic compounds, or differences in its initial composition. As it neared perihelion, the ratio began to normalize, suggesting that various layers release different substances at different times. The AI also tracked brightness changes. A network of amateur astronomers coordinated by the SETI Institute recorded a sudden brightening just before the comet slipped behind the sun. This spike exceeded forecasts and might signal a gas outburst or heightened surface activity. Orbiting observatories confirmed that the brightness persisted through perihelion. Such variations highlight the need for continuous monitoring and illustrate the value of combining professional and citizen science data. In addition to detected gases, the algorithms considered how the long journey through interstellar space might have altered the material. For millions of years, the nucleus has been bombarded by cosmic radiation and high-energy particles. AI suggests that this bombardment could modify chemical bonds and create exotic species on the surface. Moreover, in the extreme cold of space, some ice phases can transition from amorphous to crystalline, releasing heat and causing small outbursts. These processes might explain irregular brightness and unusual coma composition. The mix of rare volatiles and radiation effects makes 3I Atlas a natural laboratory for studying chemistry under extreme conditions. Improved orbit prediction. A notable finding comes from triangulating data from various points. Until September 2025, predictions of 3I Atlas's position relied on observations from Earth and Earth-orbiting satellites, leaving significant uncertainty. Between 1 and 7 October, ESA's ExoMars Trace Gas Orbiter, circling Mars, pointed its camera at the comet. AI combined those data with those from Earth and refined its trajectory tenfold. That improvement allowed other observatories to adjust instruments for better study. The analysis concludes that this AI-mediated cooperation is a step forward for planetary defense. Although 3I Atlas poses no threat, the exercise tested procedures that could apply to hazardous asteroids. ESA AES planned Neomir mission aims to position an observatory between the Sun and Earth to detect objects approaching from the solar direction. AI evaluated how data from missions at various orbital positions can be combined with predictive algorithms to anticipate dangerous trajectories. Historical patterns and responsible speculation. Algorithms compared 3I Atlas OS trajectory with galactic models and suggested it originates in the Milky Way's thick disk, an ancient stellar population aged between roughly 3 and 14 billion years. If so, the object would predate our 4.6 billion-year-old solar system. This conclusion comes from its arrival direction and velocity. AI finds that its CO2-rich composition correlates with formation in a low metallicity environment. As for its ejection, models show that gravitational interactions with giant planets or companion stars can launch comets at escape speeds. AI simulated many hypothetical encounters and found that moderate-sized objects can be expelled fairly often. It also estimated the travel time through interstellar space, concluding that 3I Atlas has wandered in darkness for hundreds of millions of years. The analysis weighs orthodox and fringe ideas. The accepted view sees 3I Atlas as a natural comet, ice and rock from another system, without technological signatures. More speculative hypotheses from researchers like Avi Loeb suggest some interstellar objects could be alien probes or technology remnants. AI examined those ideas and notes no evidence of artificial engineering in 3I Atlas. It has an active coma, typical composition, and no unexplained maneuvers. Still, AI emphasizes that exploring even remote possibilities encourages curiosity. To place 3I Atlas in context, algorithms compared its behavior with the two previous visitors. 1I Oumuamua, discovered in 2017, showed no visible coma and its acceleration had anomalies attributed to undetected gas release or radiation pressure. Its elongated shape and changing brightness sparked debates about its nature. Tuyui Borisov, found in 2019, behaved like an ordinary comet with abundant water and dust, though its chemical ratios differed from local bodies. AI notes that 3I Atlas, with its CO2-rich coma and metal imbalance, adds another data point in a growing spectrum. Overlaying data from all three visitors, algorithms find no single profile for interstellar objects, hinting at diverse formation conditions in other planetary systems. Future Prospects AI highlights how this comet serves as a test case for future missions. The planned Comet Interceptor mission will send a spacecraft to wait in space for a new comet, then intercept and study it up close. AI assesses that intercepting an interstellar object requires careful planning and resources due to their high speeds. It also notes that the Vera C. Rubin Observatory will dramatically increase detections of such objects. Its wide-field cameras, combined with machine learning algorithms, could spot dozens of visitors each year. Beyond remote observation, AI speculates about sending fast probes to collect samples. Achieving that would demand advanced propulsion, electric or fusion engines to match these visitors' velocities. Models suggest that a mission launched years in advance could use gravity assists from Jupiter or Saturn to achieve the necessary speed. Although these ideas are still conceptual, AI stresses that every interstellar object offers a unique opportunity to test cutting-edge technology and refine our understanding of deep space. Conclusion and reflection. Artificial intelligence has helped us uncover patterns and correlations across diverse data. Ground-based observations, orbital telescopes, chemical spectra, and dynamic simulations. Applying these algorithms reveals details that might otherwise be overlooked. A CO2-dominated composition, an unexpected metallic ratio, a likely origin in the galactic thick disk, and opportunities to improve orbit prediction using Mars-based data. These findings teach us not only about 3I Atlas, but also about our ability to comprehend the cosmos through AI. As this comet recedes into deep space, it leaves a trail of questions. How many other interstellar visitors will cross our system in coming years? What will they tell us about the variety of planetary systems and their formation processes? Are we simply witnessing a natural messenger ejected from its home, or glimpsing a piece of a more complex galactic puzzle? AI has illuminated part of the path, but the mystery remains. We invite you to ponder and join us as we follow future cosmic travelers. Are we looking at a mere accident, or at something AI is only beginning to grasp?